let's try another example. Show that the sum of a certain number of odd numbers, so 1 plus 3 plus 5, all the way to 2n minus 1 is equal to n squared, given that n is an element of a positive integer. So using our rules of induction, we start with the first step. Show that, this is denoted, this equation is denoted by Pn. So show that P1 is true. Left side, right side, check. Left side equals 1. Right side equals 1 squared, which equals 1. So left side equals right side, check. P1 is true. Step 2. We assume this formula is true. Assume formula is true for some value k. For k. So, in other words, assume that pk is true. And to show this, we rewrite this formula, except now instead of n, we have some value k. We are not sure what this value k is, because we're assuming that whatever value k is, this formula is correct. So we have shown P1 is true. We assume that this formula is true for pk. And now let's show that let's show that with our assumption that pk plus 1 is true. To do this, we have a left side and a right side. So right side here would just be k squared, k plus 1 squared. K plus 1 squared. Left side will be 1 plus 3 plus 5 plus all the way to 2k minus 1. And then plus the next term, which would be 2 times k plus 1 minus 1, which becomes 2k plus 1. So that's our left side. And let's try simplifying the left side. 1 plus 3 plus 5 all the way to 2k minus 1. Why? That's just k squared. So let's simplify that. K squared plus 2k plus 1, which we can factor to equal to k plus 1 squared. Or let's say, for some reason, let's say you forgot how to factor, what we could do is expand the right side, expanding k squared multiplied by 2k plus 1. So left side equals right side. In this, our induction is complete. Well, almost complete except for concludes statement. The first term is true. If a term is true, then the next term has to be true. Therefore, since the first term is true, the second term has to be true. And so, because the second term is true, then the third term has to be true. And because the third term is true, the fourth term has to be true, and every successive term is true. So to write this, we say that since P1 is true, and pk plus 1 is true whenever pk is true, then that means Pn, this formula, is true for all n is an element of positive integers. So just to recall, Pn is the sum of all the odd numbers is equal to a perfect square. So we've proven that with induction. Of course, we could have also proven this with geometrically. For example, let's draw this out. So 1, this is where we have 1 plus 3. 1, 2, 3. Oh, look at this, side length of 2. 1 plus 3 plus 5. 1, 2, 3, 4, 5. Oh, hey look, this is equal to 3 squared. 1 plus 3 plus 5, let's try plus 7. 1, 2, 3, 4, 5, 6, 7. Oh wow, 4 squared. So we can also have proven this geometrically. Induction. And that's one of the great aspects of math. There are multiple ways to prove one formula. You can use multiple very different ways to arrive at the same result. So that's one example. Let's try one more example. Show, that 1 cube plus 2 cube plus 3 cube all the way to n cube is equal to n times n plus 1 divided by 2 squared. So what this means is that the sum of a certain number of cubes is equal to the square of a triangular number. We use induction. So step 1, let this equation be denoted by Pn. Step 1, show that P1 is true. So left side is equal to 1 cube, which is equal to 1. Right side is equal to 1 times 2 divided by 2 squared, which is equal to 1. Left side equals right side. Therefore, P1 is definitely true. 2. We assume that this equation, this formula is true for some value k. Assume pk is true. So 1 cube plus 2 cube plus 3 cube all the way to a certain number, k cube, is equal to k times k plus 1 over 2 squared. Okay, so with our assumption, let's proceed to show that pk plus 1 is true. So left side is equal to 1 cube plus 2 cube all the way to k cube. Okay, yeah. The algebra is going to might be a bit ugly. Right side is equal to k plus 1 times k plus 2 over 2. Ooh, the writing here squared. So left side, hey look, this is equal to k times k plus 1 divided by 2 squared. So let's use that. Recall that we must always use our assumed pk case inside the pk plus 1 case. So here we put that right in, k times k plus 1 squared plus k plus 1 cube, which we can simplify. We have k squared plus k squared. I first squared the denominator, first squared the numerator in the next step, plus k plus 1 cube. This is k cube plus 3k squared plus 3k plus 1. If you didn't know that, that's fine. You could also expand the k plus 1 cube and you'll arrive at the exact same equation. How I did it here was basically memorization. You could also have used the binomial theorem, which I'll explain in a later tutorial. So here, let's bring everything over 4. So k squared plus k squared is equal to k to the power of 4 plus 2k cubed plus k squared. Basically, what I did was square this term, and then square this term, and then plus 2 times this term times this term. If you don't know that shorthand, it's fine. Go ahead and expand that, and then you'll find the exact same result. Plus 4k cubed plus 12k squared plus 12k plus 4. We collect like terms, so k4 plus, okay, these two are the same, 6k cubed plus these two terms, 13k squared plus 12k plus 4. Okay, so right side, k plus 1 times k plus 2, that's k squared plus 3k plus 2 over 2 squared. The algebra is going to be a bit heavy. Of course, we could write this another time. So k squared plus 3k plus 2 over 2 times k squared plus 3k plus 2 over 2, and then expand it like that. But I'm going to take a shortcut. You might find it interesting on how I'm going to do this. So square the first term plus square the second term, square the third term, and then, oh, this is all over 4. 2 times k squared plus 3k, that's 6k cubed, plus 2 times 3k plus 2 times 2, which is 12k, plus 4k squared. And this simplifies after collecting left terms. Your math teacher is not going to like my form. Is equal to k cubed plus 6k, k fourth plus 6k cubed plus 13k squared. The k squared terms are over here, plus 12k from here, plus 4 all over 4. So left side is equal to right side. Therefore, since we have shown that P1 is true and PK plus 1 is true, as we have shown because the left side equals right side, whenever PK is true, and we know that there does exist such a value PK is true, which is when K is 1, then that means Pn, this formula, is true for all values of n that are positive integers. So this is a rough overview of how to do induction, how to use induction with algebra. We show that the first term is true, we assume that this formula is true, and with that assumption we show that the next term has to be true. Therefore, since the first term is true, the second term has to be true, and so on, everything is true. So I'd like to end this tutorial with several questions that I encourage you to try to think about. So first, does induction work in formulas whose n values are not integers? Here, n is an integer. What if n is not an integer? Can we use induction in formulas that contain imaginary numbers? And finally, what happens if, when we try to show that k plus 1 is true, so in this step, when we try to show that it's true, the left side does not equal to the right side. Thank you for watching, and I hope to see you in my next tutorial.